What's going on, everybody? It's High Peak Education coming back at you with a angular momentum question. So I'm going to perform this calculation, see if you can hopefully follow along. An ice skater is spinning at 0.800 revolutions per second with her arms extended as below. Her moment of inertia with her arms extended is 2.34 kilogram meters squared. Her moment of inertia with her arms close to her body is 0.363 kilograms times meter squared. A, what is her angular velocity when she pulls her arms in? B, what is her rotational kinetic energy before and after she pulls her arms in? C, where did the rotational kinetic energy come from? Okay, so here is the ice skater with the arms extended. She has a large rotational inertia. So this is going to be I, initial, and that's 2.34 kilograms times meters squared. That's her initial rotational inertia. Notice her final rotational inertia should be 0.363, that's given, kilograms times meters squared for the units. Notice, again, when her arms are inward, she has a less overall radius, so her rotational inertia is less. Now, how do we know this is the conservation of angular momentum? Her angular velocity is going to change because her rotational inertia changes. And intuitively, if the radius gets smaller, you've seen ice skaters probably do this before, she spins faster. She does have a torque, but her torque is internal. So if there's no external torques, if all the torques are internal, then any torque that's on her came from the fact that it was an internal torque. And so just like linear momentum is conserved in the absence of external forces, rotational momentum, or angular momentum, is conserved in the absence of external torques. Part of the reason an ice skater is a good example of this is because as she spins without much friction on the ice. So all the torques are internal from her changing her own radius. So we also know what her angular velocity is when she begins. It's 0.8 revolutions per second. Now let's go ahead and get that. That's the initial angular velocity, 0.8. And that's, again, revolutions per second. Now notice we could calculate her final angular velocity in revolutions per second, but in order to get her rotational kinetic energy, we need this in SI units. So we might as well get rid of revolutions and go to radians. That's the SI unit. And for every one revolution, there's 2 pi radians. Okay, because that's the unitless angle for one full revolution. Okay, so we multiply this out. We have 0.8 times 2 times the pi key, and we'll approximate this. It's about 5.03 radians per second. Okay, so there it is. That's the approximate initial angular velocity. Now again, let's use the conservation of angular momentum. Remember, the conservation of angular momentum comes from the fact that there are no external torques, there are only internal torques. So let's write down the conservation of angular momentum. That's L initial equals L final. By the way, this is not a length, it's sort of angular momentum. You could give it a slightly different L symbol, but capital L is what's most typically used. So rotational inertia times angular velocity is angular momentum. So let's put the subscript capital I subscript lowercase I omega subscript I equals I final omega final. And we could solve this for omega final. By division, I initial omega initial over I final is equal to omega final. And let's put the numbers in. So the initial rotational inertia was 2.34 kilograms times meters squared. Her initial angular velocity is 5.03. That's radians per second. and then we divide by the final rotational inertia, 0.363 kilograms times meters squared. So let's get this number. So alpha fraction stack, numerator over denominator, 2.34 multiplied by 5.03 and divide that by 0.363. There we are. And that should be 32.4, and that's going to be radians per second. So 32.4 radians per second. And let's think about why this is the correct answer. Notice her rotational inertia is many times less. So it's certainly less than a quarter, and however many times less her rotational inertia is, then that's how many times her angular velocity goes up. So this looks like a little bit more than a factor of 6, because 5 times 6 is 30, so this is a little bit more than 6 times smaller rotational inertia. Okay, so that solves part A. Let's take a look at part B. So part B says, what is her rotational kinetic energy before and after she pulls her arms in? So before is her initial kinetic energy, and that's her rotational kinetic energy, and that's going to be 1/2 I initial omega initial squared, whereas her final rotational kinetic energy should equal to 1/2 I final omega final squared. Okay, so we can put those numbers in directly. That's 1/2 I initial was 2.34 kilograms times meters squared. Her initial angular velocity is 5.03 radians per second, and we square that. And then 1/2 I final is 0.363 kilograms times meters squared, and then her final angular velocity is 32.4 radians per second squared. Okay, so let's get her initial rotational kinetic energy approximated, and let's get her final rotational kinetic energy approximated. So her initial should be 0.5, that's a half, times 2.34 times 5.03 squared. So that is 29.6, and that's joules. All right, let's perform the same calculation but with these different numbers for her final rotational kinetic energy. So this should be, and we can just go 0.5 times 0.363 times 32.4 squared. So this is 190, and that approximates to 191, 3 significant digits, 191 joules. All right. Now the question is, where did the rotational kinetic energy come from? Now think about this. Her angular momentum is conserved, but her rotational kinetic energy is not. So the only way that there's an increase in kinetic energy is that if positive work is done. Where did that positive work come from? It came from her muscles. How do I know that? Because she's forcing her arms over a displacement inward. So remember, work is like force times displacement. So we can say the following. We can say her rotational kinetic energy increases due to the work done by her arms forcing mass into the center at a smaller radius. Okay. Now, by the way, you may wonder, why is this no external torque? Well, because the system we've defined is just the girl, and in some sense, you can imagine sort of the sum of her body parts is the system, Because again, if those body parts go inward, okay, the idea is that there's no change as far as any external torques, all the torques are internal. There can be a change in energy, there can be work done, but just because momentum is conserved doesn't mean energy is conserved. Alright, so that ends this problem. And thank you very much for watching High Peak Education. Please smash that like button if you enjoy this content. Please subscribe to the channel in order to grow the channel. I look forward to reading your comments, and I look forward to seeing you in the next video.